The universe has always been an interesting place, ever since its birth, and it still is. Why? Why is the universe such a dynamic place doing these wonderfully intricate things like making stars and planets, galaxies and clusters, polar bears and people? The answer has to do with energy, how it gets around, associating itself with different things. In this episode of SpaceTrek, we are going to do some accountancy. We'll be tracking some important transactions that happen in the universe and try to figure out why they happen, with the hope of figuring out something relevant to our original question. Oh, and by the way, these won't be transactions involving money. These are going to involve energy. Don't worry, you won't need ridiculous counting skills to keep up. Complex things, like us, need energy to do what they do. Where do our bodies get the energy to perform all the necessary everyday tasks that keep us alive? Food, sure, but where do we get our food? Other living things, plants and animals most of the time. Maybe some fungi thrown into the mix. Plants get all their energy directly from the sun. Okay, not completely true, but we'll get back to that. Most animals also get their energy indirectly from the sun. That is, they either eat plants, or other animals that eat plants, or other animals that eat other animals that eat plants. You get the idea. Fungi just feed off the rotting remains of plants and animals, so they're also indirectly powered by the sun. Oh, and remember I said that plants get all their energy directly from the sun is not completely true? Well, some plants are a bit unconventional, like insectivorous plants. But then again, insects are indirectly solar powered, so while all plants may not be directly solar powered, they are exclusively powered by the sun nonetheless. The point here is that we, along with most plants and animals, are completely solar powered. Now, you'd want to extrapolate that all life on Earth is solar powered. Well, that's not quite true. Deep in the ocean, there are these microbes that are chemosynthetic. They get all their energy from hot, noxious gases that are dispensed out of hydrothermal vents at the bottom of the ocean. They survive in a cycle that is completely independent of the sun, and get their energy from the Earth's thermal activity instead of the sun's heat. If the sun suddenly stopped existing, they wouldn't even notice. Although, in hindsight, they wouldn't even notice that there was a sun in the first place. Best case scenario for humans without the sun? We might not even be able to survive for a couple of years. But chemosynthetic bacteria, they would survive not for years, not decades, not centuries, not even millennia, but literally billions of years. And they wouldn't just survive, they would thrive. Anyway, all life on Earth may not be exclusively solar powered, but the vast, vast majority of it is. The sun. The sun's power is hard to comprehend. The energy that it generates per second is equivalent to the amount that would be released if you were to detonate 1.8 billion SAR bombs simultaneously. It generates energy via nuclear fusion in its core. All those octillions of tons of gas and plasma have a lot of gravitational potential energy. Those layers are crushed under their own weight by gravity. That's what ultimately keeps the fusion in the core going. So there, the most complicated thing in the universe, life, mostly ultimately gets all its energy from a star. A furnace that'll keep radiating more energy, more food for us, for a very long time, as a result of the physical conditions in its core that are maintained by its enormous mass being crushed under its own weight. Now, you could stop here and be satisfied, or you could ask why we get to enjoy the presence of this benevolent star that showers us with all the bread and butter we need. Why the sun exists in the first place. At this point, we'll have to step up our game. This tracking of energy balances will have us traveling to the past for the first time so far. All the way back to the birth of the sun. Stars are made in factories called nebulae. A nebula is what is left of the outer layers of a star, a very big star after its death. Stars that are massive enough end their lives in huge explosions called supernovae. These are some of the most powerful events in the entire universe. This is an image of another galaxy. That bright spot there might be mistaken as a star in our own galaxy that got caught in the frame. But it isn't. It's actually a supernova in that galaxy. It's able to rival the glow of that entire galaxy, hundreds of billions of stars. Calling supernovae powerful is understating it. After a star blows its guts out into space in one of these massive explosions, those outer layers of ionized gas, now expanding into the surrounding space, are rendered aglow, with each element glowing with a different color. These gas clouds are denser at some places and rarer at others. Gravity pulls the denser parts of these clouds in on themselves, building up the pressure in the middle. Eventually, this collapse ignites the nuclear furnace in the heart of the cloud, and a star is born. This is how our sun formed, from the remains of a star that ended its life in a supernova eons ago. That cloud of gas that eventually became our sun is to this day converting matter into energy via nuclear reactions that were jump-started by its gravitational collapse. The matter inside the sun gets converted into the energy that it radiates out into space. So, keeping track of all those energy exchanges has led us to matter itself. At this point, you could ask why there is matter in the universe in the first place. Why doesn't the universe just contain photons drifting through the vacuum of space? Instead, for a moment, let's take the existence of matter as a given, and ask what started everything. How were the very first stars born, which would later be responsible for the birth of more generations of stars in the future? Why couldn't the universe just stay dark, full of gas, and uninteresting? For about 100,000 years after the Big Bang, the universe was a dark place. There were no stars, just gas spread uniformly throughout the universe. The density and temperature of the universe were very uniform in the early days, where departures from perfect uniformity were only 0.003% or so. This baby picture from the Planck satellite shows fluctuations from perfect uniformity, with the red hot spots corresponding to the underdense regions and the blue cold spots corresponding to the overdense ones. The gas in the overdense regions collapsed in on itself due to gravitational effects, and eventually the pressure in the middle became significant enough to kickstart nuclear fusion. That's how the very first generation of stars was born. But what if even that 0.003% departure from perfect uniformity didn't exist? What if the early universe were perfectly uniform? Even if that were the case, it wouldn't have stayed that way. The random motions of molecules would eventually have led to a little too many molecules bunching up in an area here, a little too many leaving an area there. Random motions would have led to a slight non-uniformity, which would then get amplified by gravitational effects. Denser areas would pull in more stuff, getting denser still. This sounds like a violation of the second law of thermodynamics, doesn't it? It is. The second law states that the net entropy of the universe can never decrease. In other words, in the context of our perfectly uniform universe system, you can't just have the emergence of non-uniformity on its own. But you can. The second law isn't really true all the time. It only gives us a statistical rule of thumb that is true most of the time on larger scales in complex enough systems. There's loads of situations where it's violated. Okay, so as long as there's matter in the early universe, star formation is bound to take place. So let's get back to the other question. Why is there matter in the universe in the first place? After the Big Bang, for a little while, the universe was hot enough for photons to spontaneously convert their energy into matter-antimatter particle pairs, which immediately thereafter annihilated each other, returning their energy back to the photon. For unknown reasons, the symmetry between matter and antimatter was broken. For every billion antimatter particles, a billion plus one matter particles were born. The small mismatch meant that after the matter and antimatter particles had annihilated each other, leaving no antimatter behind, and the universe had cooled down so photons couldn't just spontaneously birth more matter and antimatter particles, there was still some matter left over in the universe. That leftover matter is all the matter we see in the universe today. You, me, all the stars, planets, asteroids, dust, everything. No one knows why that matter-antimatter asymmetry happened. So we don't have an answer to the question of why there is matter in the universe today. At least, not yet. We just know that there is. So, we have seen that the universe is interesting and dynamic. Energy is being thrown around all over the place. And there are these concentrated sources of energy, stars, planets, and so on, that spread their energy around, lending it to other things. Sometimes giving rise to interesting phenomena, like earthquakes, solar flares, supernovae, and even, at least on one occasion, life. And these concentrated sources of energy are a result of the slight unevenness of the almost perfectly uniform early universe, although they would have emerged without that little non-uniformity anyway. The universe is an interesting place only because of these concentrated sources of energy, like stars and planets. There are these massive energy gradients everywhere, and energy gets shuffled around like cards in an intense game of Uno. More precisely, it's because the entropy of the universe is nowhere close to its maximum value. Not yet. All that's really saying is that the spatial energy density and temperature are not the same everywhere in the universe, and that allows for flows of energy from one place to another, and as a consequence, many interesting things and wonderfully dynamic and constantly changing systems. But, like all good things, it won't last forever. Remember the second law of thermodynamics? Okay, it's not perfect all the time, but it is a very powerful law in terms of the kinds of things it allows us to predict. It tells us that the entropy of the universe will keep increasing with time, marching off relentlessly towards a maximum value. What that means in English is that the universe will die one day. One day, these energy gradients will not exist anymore, and the temperature of the universe will be the same everywhere. One day, there will be no more stars, no more galaxies, and not even any further scope of any more of those things forming. And sure enough, we see that as the universe gets older, fewer stars are formed than however many die. That's because not all stars end their lives in a way so as to provide nurseries for new stars to form. In fact, a very small minority of them do. We are fully aware of what the future holds on this scale, even if we're not absolutely certain of the more distant parts of this future. And I'll say this right now, it won't be pretty. It'll be depressing. And it will all start with our era of starlight coming to an end, when there will be no more stars in the universe anymore, and no new stars will ever form. We'll get back to this view of the future in a different episode of SpaceTrek, so stay tuned if you think this stuff is for you. For now, don't worry about it. That's all so far into the future that it doesn't even matter for anybody. The important thing is, the universe has only just begun its life, and we are living in its golden days, the era of abundant starlight, an age perfect for the exploration of that vast ocean of stars, planets, and so much more. As for now, we have reached the end of the line for this episode. We have seen how the present entropic state of the universe makes it a dynamic place doing very intricate things, and how this present situation is tied to those small yet significant events of the distant past. In the next episode, we'll talk about the empire of the force of gravity, which is, as we have seen in this episode, extremely significant in determining how the universe behaves on a large scale, as well as its large-scale structure. For now, though, keep looking up.